Okay, good morning. All right, you should have gotten an email about quiz 1 from Gradescope. So, and I mean, we're just kind of working out the kinks here, so I'm not too worried about grades and such, because I'm still trying to figure stuff out. So I'm happy to be kind of generous. So I did kind of make some quick notes in the Gradescope markings. So check that out, and you know, if I saw some mistake, then I pointed that out. If it looked good, then it's just marked as correct, even though, you know, the answer might not be correct from WebAssign, but the work looks pretty good. So then something just kind of minor happened. We'll have another quiz on Friday, but as it looks right now, it's going to be pretty 1.5 heavy. So we're going to finish 1.5 today, and then I'm hoping to get into 2.1, but we'll see. Okay, so a couple of things I did was I completely dropped the last question on the quiz, because no one did it, I think. Or anyways, it was just nice to drop it. And then I also dropped the marks, not your grades, but the worth of question 6. So I made the WebAssign quiz out of 18 instead of 28. You kept all your marks. So that boosted some of you over 100%, which is great. I'm fine with that. And then I incorporated your work. Okay, so as we move through the term, the emphasis on your work is going to get heavier and heavier. Right now in the first few sections, you know, it's mostly review, so I'm assuming that it's pretty good, but as we move through, right, I'm going to start shifting the emphasis of your grades to your work. Okay, so make sure that you're showing everything and giving me all that good stuff. So we've got quiz number 2. Quiz number 2 on Friday. Okay. What I want to do, let's just start it right at 10. Okay, so, and I also want to kind of, maybe not pull you here, but I do want to see if maybe you would want to, instead of having it during class time in a specific time frame, if it's just a timed quiz that you could do anytime on Friday, that's something that I'm kind of thinking about. Because I don't know, I find it a little bit restricting to do it in class time when we don't really have to. But so that's something that I'm thinking about. But for quiz 2, we'll do it during class time, just like we said we would. It will be from 10 to 10:45. Okay, it's going to be quite a bit shorter. I realized that quiz 1 was pretty long. So you'll have 45 minutes, and it's going to be on sections, section 1.5, and as far into 2.1 as we get today. A lot happened though in 1.5, right? So just kind of be prepared for that. Okay. Same idea. Quiz is going to go up on WebAssign. You'll do your work on the side. You'll scan it. You'll upload it to Gradescope, and that'll be good. Okay. So I'll try to keep it nice and short this time, or relatively short. So for review, unless there are questions, but I guess I should pull up the chat here. Nothing. Oh, my mouse isn't there. Just for some review, right? One-to-one functions have inverses. So one-to-one functions, oops, can't write at all today, yikes. It's usually not a good sign. One-to-one functions have inverses, right? And the inverse maps an output back to an input, right? And so that's why it has to be one-to-one. And we talked a lot about one-to-one last day, so that's why I'm kind of leaving it. But it's just saying that for each input, I can only have one output. So one-to-one functions have inverses, and the inverse function maps an output back to an input. And just to kind of clarify, usually an output, we call it y or f of x, and then the input is usually x, right? Or another common input is t if we're talking about time, but usually it's just x. So we talked about one-to-one functions. We talked about how do we show that it's a one-to-one function. I'm going to leave that in the past. And then how do we actually calculate the inverse function is kind of where we ended off. And so what you do is you solve for x. And so in solving for x, you're reversing the function. So now you have x as a function of y, right? So x as a function of the output y. So that's how the inverse works. We also talked about how to confirm that what you have is in fact the inverse, right? Using those cancellation properties. And so we said that f composed with its inverse should return just x, right? And also the inverse composed with the original function should also compose to x. So this is how you check to see if the inverse that you found is in fact correct. And we went through all the steps with one example. This is something that should have been done in a previous course, whether that was pre-calculus or grade 12 or whatever. So that's why we're not spending a ton of time on it. But the textbook does review it more. So if you want more. All right, so continuing in section 1.5, the next part of 1.5 is on logarithms. And you might wonder why logarithms are in the inverse function section. That's because the logarithm is the inverse of an exponential function, right? And so logarithmic functions, and we're reviewing all this stuff just because we'll need it later on in the course, right? We'll need to know log laws, for example. We'll need to know what the inverse is and what it means. So we'll be relying on this later on. So just knowing about these functions, that's why we have to review them. So logarithmic functions, logs, as we call them typically, logarithmic functions. It's a little bit long to write. So logs are the inverse of exponential functions. So exponential functions, right? An exponential function might look like b to the power of y equals, b to the power of x, equals y. I was jumping ahead a little bit. Okay. So typically that's the look of an exponential function. A logarithmic function can have any base. And so here we talked about the exponential function with a base of b, right? So here, oops, we can have a base b. So that's why we just left it as a generic exponential functions for any base, right? And so now what we're gonna say is I'm gonna bring in that little blurb from here. Okay. So what we have is the log base b, and you should have worked with logs in the past, so hopefully this is review. Log base b of x is equal to y is the same as saying b to the power of y equals x. Now notice that this is slightly different, right? Because here we're treating this inverse function as if it's the original function, but the structure is the same, right? So log base b of x equals y is the same as saying b to the power of y equals x. So sometimes, right, how you'll want to solve these is if you're solving a logarithmic function for y, you might have to think to yourself, okay, b to the power of what equals x? And that's a little bit backwards, right? But if you kind of get into this swinging motion of b to the power of y equals x, then sometimes that'll be the way to solve these logarithmic functions. We're gonna have more sophisticated ways of solving these. So if that doesn't make sense to you, then don't worry about that, because we'll just have rules that we can follow to solve logarithmic functions. But technically that's what's going on, right? B to the power of y equals x. And so you should be able to use that to solve for x or y. One important thing here is the following, and I'll make it kind of, I'll highlight it here. This is the same as saying, if you take the inverse of the original function, you get back to x, right? And if you take the original function, the exponential function, and compose it with the inverse, right? Then you should get back to x, right? So this is the same as f of, well, I guess f inverse of f of x should equal x, and f of f inverse of x should equal x. We've got an extra restriction on the domain of a logarithmic function. And so I want you to make a note of that, because in addition to, okay, we can't divide by 0, we can't take the square root of a negative number. Now I need you to add, okay, I can't take the log of 0 or a negative number. So I can only take the log of a positive number. So that excludes 0. I need you to add that to your kind of domain roster. Okay, so domain. We cannot take the log of 0 nor a negative number. Oops, number. Okay. So this will factor into our domain calculations, right? So we need to remember this when finding the domain of logs. So that's going to be really important, right? So just here, that's why we have for every x greater than 0, because here you're putting an x into a log, and you can only do that for positive numbers, right? But it should return x either way. Okay. So how can we apply this, right? So what this is saying is that if you have an x in the exponent and you need to solve for it, right? So bring it down. One way that you could do that is you could take the log of the same base as your exponent, and then you would just be left with x, right? So this is essentially a cancellation property, right? Which is what these are too, but here it's more kind of applied. And same thing, if you have an x inside a log of base b, if you raise it to the power of b, right, both sides to the power of b, then what you're left with is your x, right? And so here, I like to think of them as undoing, right? So if you need to solve for x in an exponent, maybe I shouldn't say undo. To solve for x in an exponent, that's more proper. To solve for x in an exponent, we use the fact that, and I'm going to grab this first one, the log base b of b to the power of x equals x, in order to bring that x down from the exponent. Right? This is saying we take the log, and I'm going to go one step further. Technically, using log laws, which I'll introduce in a little bit here, you can technically take any log base. Okay, so you can use any log base to bring this x downstairs, but if you wanted to just shake out the x, you'd have to use the same base. So we would take the log of the same base to bring x down from the exponent. Okay. Similarly, to solve for x inside a log, right, we use this fact, right? So here, x is inside a log. So what I've done is I've raised both sides to the power of b, the same base. And then on this side, I'm left with just x, right? So to solve for x inside a log, we raise it to the power of the same base, right? B to the log base b of x equals x. Okay. And I've got a couple examples in a little bit here, but we're going to move on to the natural log, which is going to be pretty useful. But first, let's talk about the laws of logarithms here, because we'll need these. Okay, so if x and y are positive numbers, again, we can only take the log of a positive number. And from here on out, when we say positive, it excludes 0, right? So especially if we're talking about logs, sometimes it can be kind of context dependent, right? But especially for logs, if we say positive, we're excluding 0. So log base b of x times y, you can rewrite as log base b. So the base stays the same, but you can split it up by adding those log of x plus the log of y. So multiplication turns into addition, and addition moving the other way turns into multiplication inside the same log. Notice that you have to have the same base, right? So this is how we're going to simplify logarithmic functions in order to work with them. Same thing, if you've got subtraction here, then it becomes division inside that combined log. And if you've got division inside, you can split it up by subtracting. Okay? Now here, this one we're going to use a lot, okay? Because a power on the x inside a log, you can rewrite, so this is equivalent to r times the log of x. Notice that this is how we're going to shake out just an x, right? So usually you'd have to move this r out front, but knowing that it's equivalent, right, that's an equivalent statement is going to be really useful. So let's see here. Let's do a quick example before we move this up here. Keep it on one page. Okay, so if we have to evaluate log base 2 of 80 minus log base 2 of 5, the first thing I'm going to check here, because likely what I want to do is I want to compress it and write it as a single logarithm. The only way I can do that is if I have the same base. I have log base 2 in both cases, so that's good. So I'm going to write log base 2 of 80 minus log base 2 of 5 is the same as property number 2, or log law number 2, log base b, right? In this case, b is 2, x is 80, and y is 5. So I can rewrite this as the log base 2 of 80 divided by 5, which is the same as the log base 2 of 16, right? 80 divided by 5 is 16. I don't know that, but I have it in my notes already, so cheating. Okay, so if we want to evaluate this, right, we need to figure out how do we solve for this, and there's going to be, like I said, we'll have other ways of doing it than this. So if what I'm about to do doesn't really make sense, then that's okay. But what I'm going to do is I'm going to take this and just remember, okay, that, where is it? Here. Ooh, just catching up, okay. So what we have is the log base 2 of 16 is equal to y. Okay, so what I want you to do is think about, okay, well, 2 to the power of, so I'm looking over here, but I'm kind of mapping it from the first one here. So 2 to the power of what equals 16, right? And so here, I'm going to copy that down here. And, right, so from here, I've got log base 2 of 16 equals y, right? Which is the same, so kind of just mapping it back and forth here, which is the same as 2 to the power of y equals 16. Trial and error gives us that y must be 4. By trial and error, right? I just want to make that note because sometimes it's not obvious what we were doing. And so I just want you to know that this was just by trial and error, right? You try 2 to the power 3, 2 to the power 4, hey, you got it, right? So then therefore, log base 2 of 16, if we had to evaluate it, must be equal to 4. Okay. Good. So that's one way that you could evaluate these logs. like I said, we'll use those log laws more and more. First, I want to talk about the natural logarithm. You might remember the natural log. The natural log is the special log, log base e, where e is just an irrational number, 2.7, blah, 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 blah. And what we'll find later on in the course is we like to use e, and most fields only use log base e. I think maybe physics might use log base 10 sometimes for, I want to say electricity uses log base 10, but I'm not sure. But most fields use log base e as their kind of default log. Now, for that reason, whenever I say log, usually I'll mean log base e. And I know that's really confusing in the beginning. I know that because I had a prof who did the same thing to me. And I thought, man, he's so crazy. Why can't he just call it ln or ln or whatever? But I get it now. So we'll get there. But so if you catch me saying log, I try to say ln or ln, but sometimes it slips out. Often it slips out, I should say. So the natural logarithm, so most disciplines use a log base e, okay, which we write as ln, right? Or if you're me, I usually do like a script ln, because you end up writing it a lot, right? So usually that's how I end up writing it. So I want you to be able to recognize it, right? But ln is just the shorthand for the natural log, called the natural log or logarithm. Okay. We talked about e as a number a ways back. E is special because it has a slope of 1 at x equals 1. I think it's x equals 1 or y equals 1. Anyways, at some point it has a slope of 1, and it just makes a really nice, we talked about it and now it's escaped me, but that's okay. But it's got this nice property, and so that's why we use it, especially in calculus. We'll use log base e most of the time. Those log laws that we established, right, they're open to any base, right? So they still apply for log base e, definitely. And so you can still use these for any log base, but for us specifically, we'll probably stick to log base e most of the time. So I've got a couple of examples for us to go through, quite a few actually, right? And so here, I'm just gonna work through some different scenarios here. So find x, I'll make this a little bit bigger here. Find x if the ln, so the natural log of x, is equal to 5, right? So here, if you scroll back or kind of go back to what we were saying here, to solve for x in an exponent, right? That's not, oh, it's still catching up, sorry. We take the log, and to solve for x inside a log, we raise it to the power of the same base. So now, right, we're gonna apply these. So how do we solve for x when it's inside a log? We raise it to the power of the base. And if the x is inside the exponent and you have to bring it down from the exponent, then we take the log, which we'll do in the next one. So what we've got here is we've got the ln of x is equal to 5. Okay. And so just make a note here. solve for x inside a log. Okay. So what I do is I look at the base here. This is a log base e, and then I use the property that that we established here. Where is it? Yeah, here. B. Oh, I gotta stop scrolling so much. Slow my scroll. B to the power of log base b of x is just going to drop down to x. I have to do it to both sides though, right? So if I have log base e in this case, right, then e to the ln of x is equal to x. So what that looks like for us, right, is I'm going to have e to the ln of x is going to be e to the power of 5, right? I have to do it to both sides. Okay. But that's how I cancel this, right? E to the ln of x by that property that I just scrolled away from, this drops down to x. The e to the power of 5 just stays e to the power of 5, right? So then x is e to the power of 5. Just as a note, this is the exact answer, right? And so if you want an approximate answer, now I'll just make a note here. This is the exact answer. If you want an approximate answer, right, we can use our calculator, e to the power of 5. Oh, what was I doing here? Clear all. To do e on this Desmos calculator, we have to use the functions here, okay? And then it's got this e to the power of x button, right? And so e to the power of 5 is roughly 148.413159.1. Okay. But just remember that that's an approximation. So 148.4131591. And this is an approximate answer. Sometimes we'll need the approximate answer, especially if you have to plot it, right? Plotting e to the power of 5 is very difficult, but plotting 148.4, for example, should be pretty breezy, right? Or relatively easy. Okay, so that's an example of solving for x when it's inside a log, a very basic example, but it shows you kind of the ropes, right? You look for the base and then you raise it to the power of that same base, and then the x drops out. Okay. Let's do another example here. Copy. Okay. So this is the example of kind of going the other way, right? So now x is up in the exponent, right? And I need to bring it down and solve for x, right? So solve the equation just means solve for x, okay? So what we have to do is we have to use the fact that, okay, I can take the log, right? So just as a rule, if you have to bring an x down into kind of our main playing field here, right? Up from the power down to, I don't know, I just think of it as our kind of main level, right? If you have to bring the exponent downstairs, you're gonna take the log. And it makes it easier if you use the log of the same base, because then they'll cancel out. And I'll show you why. But really, if this wasn't e, if this was 4, I would still use log base e instead of log base 4. So we'll see some more examples like that. But for now, we've got e, so I'm going to use log base e. So I've got e to the 5 minus 3x equals 10. solve for x in the exponent is what we're doing here. Okay. When I take the natural log, the ln of both sides, right, this looks like ln of e to the 5 minus 3x is the ln of 10. Okay. Now, the key thing here is that, okay, well, first of all, log base e and then e to the power of something, just by that cancellation rule, we're just left with what's in the power here. But even if we didn't want to jump straight to that, what we can say is, okay, well, taking the log of something brings that, is equivalent to bringing that exponent downstairs, right? So this is equivalent to 5 minus 3x times the ln of e to the power of 1. Nothing's changed on the right-hand side. Okay. And this is by property, where was it? Right, that's by law number 3 here. Wow. Hey, made an arrow. Cool, but no thanks. So by property 3 here, right, that's the one that we're using. By log law number 3. Okay. This ln of e is just, you can try it on your calculator, right? But it's just going to cancel to 1 because of that property, right? If you take the log base b of b to the power of x, right? Log base e of e to the power of 1, it just becomes x, so this becomes 1 equals 1, since the log base b of b to the x equals x, right? So just convince yourself that that cancels out. Okay. In fact, usually, once I've shown that I'm taking the log of both sides, I would usually only show the 5 minus 3x. I don't bother showing the ln of e anymore because it goes away to 1, right? Multiplying by 1 doesn't do anything. Okay, so now, right, you have to remember the ln is still on the 10, right? So, but now I'm left with 5 minus 3x is the ln of 10. Solving for x now, remembering that the ln of 10, you can use your calculator, right? So clear all. And if I go to functions, the ln of, back to the numbers, of 10, bracket, 10, is roughly 2.30258, blah, 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 right? So, so whenever you have the log of a number, any base, it's just going to be a number, right? So even though it doesn't look like it, it's just a number. So, so just treat it as 1, right? But keep it as ln of 10. You don't want to convert it to a decimal because you want the exact answer, most likely. So solving for x now, we're back into familiar territory, right? And so we're going to subtract 5 from both sides. So negative 3x is the ln of 10 minus 5. So then x must be the ln of 10 minus 5. Context tells us that the ln of 10 and then minus 5, right? You might want to show something like that, just to emphasize that you don't want to do the ln of 10 minus 5, right? 5. But hopefully you're able to kind of keep that clear for yourself, right? How you write those. Good. Because we've got this negative downstairs, oh, sorry. Oh, yeah. I know, sorry, Carly, I was a little slow on the draw here. I didn't move the -3 over quite yet. Good. And how about you, Jaspreet? Is that good? Awesome. All right, good. So this is the exact answer, right? The ln of 10 minus 5 over -3. Typically what we end up doing, this -3 can actually float up top, right? You only have one, but it can kind of float around. So sometimes what we'll do is, instead of having over -3 here and keeping it as it is, this is the right answer, right? And so WebAssign would accept it. This is the right answer, but just for kind of reading solutions maybe later on, often what they'll do to kind of clean it up a little bit is float this negative upstairs and then distribute it. Okay, so then we can write this as the negative of ln of 10 minus 5 over 3, right? Just kind of floating that negative out front, and then distributing, oops, gives me negative ln of 10 plus 5 over 3. But then usually how they'll write it is 5 minus the ln of 10 over 3. So just, especially if you're looking at solutions or anything like that, right? If you ended up here and you're seeing a solution like this, just get used to manipulating it and just confirming that, yeah, what I did, it's the same, right? So we're able to move from here to here just by floating that negative around, right? And so you'll want to be careful, but like I said, WebAssign will accept this as your answer. So I usually just leave it here. I don't manipulate it that much. Depends on how fancy you want to be. This is the exact answer. And if we had to find the approximate answer, I'll just give it to you here instead of going to the calculator. X is approximately 0.899133023. That's our approximate answer. Just depends on what they ask of you. Okay, so now I've added a little example here just so we can get back into the groove of the quadratic equation, quadratic formulas to solve quadratics. Well, how am I gonna copy this here? Copy. So here we're going to combine these logs and solve for x, right? So whenever we say solve and there's an x involved, you're solving for x, right? So let's see here. Let's start. Okay. So what I have is I have the ln of x minus 2 plus the ln of x is equal to the ln of 5. I'm trying to say ln, but I'll start saying logs, sure enough. in order to solve for x, right, I've got an x in here in the first term, and I've got an x in the second term. So what I'm going to want to do is I'm going to want to simplify these logs in order to be able to extract that x. Okay? So what I can do, because I have the same base, I can combine these by multiplying whatever's inside these logs, right? So what I can do is I can rewrite this as the ln of x minus 2 times x is equal to the ln of 5. Now, here, I'm going to do a little sneak attack, and it's, I think it's called the cancellation property, but I'm not sure. But what I'm going to say is, because I've got an ln here and an ln here, what I can kind of conclude from that is that x minus 2 times x must be equal to 5, right? For these things to be equal to each other, then I can just kind of drop the ln's. But I can only do that once I've combined it to one ln on both sides, right? And so here, these guys, these cancel out.
Just to speak up for this, would it not more or less be like if you took another ln of both sides just to cancel it out?
Yeah, so technically what you could do is you could say e to the power of both sides, right? But raise both sides to the power of e, and then they would cancel out, right? So technically that's what you would do. But I think, I can't remember the name of the property, but anyways, so technically that is what you're doing, right? You're saying e to the power of both sides, and then the e to the power of ln would drop out. But also, because you have the ln of x minus 2 times x is equal to the ln of 5, then we can just jump to, well, then x minus 2 times x must be equal to 5. But you're absolutely right. Technically correct. So if I'm trying to solve for x here, I can expand this side out to get x squared minus 2x is equal to 5. In order to solve a quadratic equation, which this is starting to look like, right, I need to have it equal to 0 in order to find the roots of this function, right? And so that's when we're able to use the quadratic formula. So then x squared minus 2x minus 5 is equal to 0, right? So here, this is a quadratic. So we can use the quadratic formula to solve for x. Okay. Assuming that it's set equal to 0. Okay. The quadratic formula, in case you haven't committed it to memory quite yet, is x is equal to negative b plus minus the square root of b squared minus 4ac all over 2a. Right? Where a in this case is 1, b in this case is negative 2, and c in this case is negative 5. So now it's just a matter of plug and chug. We're going to end up with 2 solutions, right? And the reason for that is because an x squared is a parabola, right? So if I'm crossing the x-axis, I say if, because there are situations where we don't, right? For example, if you have something that looks like this, you never cross the x-axis, so then there are no roots. That can happen, right? But most of the time we have something that looks like this, so we'll cross the x-axis at 2 points. So that's why we get 2 solutions. remove this. Okay. So what we're going to find is, okay, so we've got x is -2 plus minus the square root of -2 squared minus 4 times 1 times -5, all divided by 2 times 1. Simplifying this, I get x is 2 plus minus the square root of 4 plus 20 divided by 2. Oops. So I get x is 2 plus or minus, and if you wanted to just do the square root of 24, that's totally fine, right? Just to get back in the groove of things, we can rewrite 24 as a multiple of 4 and extract that root of 4, right? So just to get back in the groove, you can definitely just go from here into your calculator. That's fine. But let's take it a little bit further and say 2 plus minus the square root of 4 times the square root of 6 divided by 2. Right? By exponent laws, oops, 24 is 4 times 6, 24 to the power of 1/2. I can rewrite as 4 to the power of 1/2 times 6 to the power of 1/2, right? Those are exponent laws that we have reviewed. So I think, yeah, pretty sure. The root of 4 is 2. So then here, 2, 2, 2. I've got a multiple of 2 in each of these. So what this becomes is x is 1 plus minus the root of 6 divided by 1. Okay. This is where I'm going to ring the alarm, okay? Because we're dealing with logs, right? We need to pay attention to the domain. Remember, logs, we can only put in values of x that are positive or give positive values inside the logs, right? And so here, be careful. We need to consider the domain. Okay. So even though x, this is a solution for the quadratic, right? And the quadratic is a product of the logs, right? But these x's that we're proposing both have to fit into the domain. So what I want you to do is I want you to remember the original function, which was the ln of x minus 2 plus the ln of x is equal to the ln of 5, right? What this says is that, okay, well then, in order for x minus 2 to be greater than 0, right? So here, x minus 2 has to be greater than 0, so x has to be greater than 2. And then here, x has to be greater than 0. Combined, right? We have to combine these conditions. So only the overlap applies, right? So the domain, therefore the domain is that x has to be greater than 2 and x has to be greater than 0. So overall, x just has to be greater than 2. And I'll do this in caps. X has to be greater than 2 and x has to be greater than 0. So overall, x has to be greater than 2. Okay. So what I want to do then is, okay, if both of these solutions satisfy x being greater than 2, not equal to 2, then great, they're both in the domain. Or if neither of them satisfy it, then there are no x's, right? There are no solutions that fit the domain. So what we're going to have is we're going to have x is equal to 1 plus root 6. And if we do that on our calculator, which I trust you're able to do, 3.449 ... That is a solution. Right? Is a solution. 3.449 is larger than 2. And the other option is x is equal to 1 minus the root of 6, which is roughly negative 1.449. Continues, but just ignoring that. That's not greater than 2, so it's not a solution. So then what we've landed on is that there's only one solution for x, and that solution is, the exact solution is 1 plus root 6, and the approximate solution is 3.449. So what I'll say here is therefore x equals 1 plus root 6. So that was a problem where we definitely combined all these log laws, but also kind of reminded ourselves of the quadratic formula and quadratic equations in general. Okay. Let's see here. I'm looking at the time. How about we do a little break? So let's do a break till, let me think of the time here. It's 12 here, 11 there, 11:10. How about that? Because that was a big problem. Break until 11:10. Pause this. Start this up again. If I move really fast. Oh, now it's keeping up. Anyways, we'll see. All right, so pretend that never happened. But it doesn't need to be in the notes. So let's do another example where we're just combining these logs, making them a little bit more complicated, just to see what it looks like. Because a lot of the time when we're solving for something inside a log, we'll have to combine these logs first. So if we have to express the ln of a plus 1/2 the ln of b as a single logarithm, what we're going to have to do is first bring this 1/2 up to the power. So being really fluent in moving this exponent upstairs onto b or down in front, right? Knowing that those two statements are equivalent, right, is going to be really helpful. So here, recall, and let me, so I don't have to scroll around so much, that the log base b of x to the power of r, just using the notation from our notes, is the same as r times log base b to the power of x, right? So just remember that those two are equivalent and we'll use them interchangeably, whatever is more convenient, right? In this case, I'm going to bring this 1/2 upstairs in order to be able to combine these two natural logs, right? Because it's logs of the same base that I can combine. So I have, oops. I have the ln of A plus 1/2 ln of B, just writing out the problem, is equivalent to saying the ln of A plus the ln of B to the power of 1/2, right? The root of B. We'll keep it as a power of 1/2 for now. This, because I have the same base here, right? I know if I'm adding the same base, I can combine them as one log by multiplying inside A times B to the 1/2, which is the same as the ln of A root B, which looks a little bit cleaner. So we've got all these log laws and everything for logs of any base, but what you'll probably notice is that on your calculator, no matter which one you're using, you probably only have a log button, which is log base 10, and an ln button. Now there are some calculators like this one here has the log of any base open, so I can specify which base. But for most calculators, you only have a log base 10 button, so it's just log, or log base E, which is ln. So most calculators only have log, which is log base 10. So that's the common log, it's called. Log and ln, which is log base E, of course, buttons. Okay. So if I go to this Desmos calculator that we're using, if I go to the functions, sure enough, I only have the ln button and the log button, right? And the log button, it's log base 10. So we need to be able to calculate logs of any base. And so for that, we have the change of base formula. So to be able to approximate, right, to find the decimal, to approximate logs of any base, we need the change of base formula. So to be able to approximate logs of any base, we use the change of base formula. Okay, which I'll grab from our notes here. Copy. So what it says is that, okay, if you want to find the log base B of X, so B could be 3, for example, log base 3, there's no log base 3 button, but what you do is that's equivalent to saying that the natural log of X over the natural log of B. Okay, and that's just a rule that we're going to use. And so let's use it in the next example here. So if we have to evaluate log base 8 of 5, correct to 6 decimal places, right here we've got log base 8, which we need to know how to deal with, right? But what I do is I convert log base B of X to the natural log of X over the natural log of B, and then I'll be able to evaluate this. So what I'm going to do is I'm going to write out the log base 8 of 5 is equivalent to the ln of 5 over the ln of 8. This is, of course, the exact answer, ln of 5 over the ln of 8. Okay, and I'll emphasize that here. This is the exact answer, but we're asked to approximate it to 6 decimal places, so let's do that. So we've got the the ln of 5 divided by the ln of 8. Making sure I have the numbers in the right order there. So we get 0.773976036. Let me copy that down here. So 0.7739760316, which to 6 decimal places is what we asked for. 0.7739123476, and I can just drop off at 6 because it's followed by a 0, right? 26. dp is decimal places, of course, which I'll use quite a bit, so I should probably specify. Great. Logs. Man, oh man. All right. So logs, remember, are the inverse. So we're still talking about inverse functions. Logs are the inverse of exponential functions. We cannot talk about inverse functions without talking about inverse trig functions. So inverse trig functions are our next stop on the tour. Inverse trigonometric functions. Okay. You might remember to define inverse trig functions, we restrict the domain, right? Because if we think about the sine function, for example, right? We notice that the sine function is not one-to-one, right? There are multiple values of x that give the same output, right? Because it oscillates between -1 and 1, and it keeps going and going and going, right? And so we know sine of x is not one-to-one. Right? If you have a look at the sine of x, sine, cosine, sine starts here at the origin, right? And then it goes up, and then it goes down, and then it goes up, and then it goes down, right? So the horizontal line test is how we check for one-to-one functions, which is probably the easiest thing here, right? And so I get 2 values, so 2 inputs that give me the same output, right? Two inputs give the same output. Therefore, not one-to-one. Okay. I'm not going to prove it algebraically because it gets a little bit weird, but with the sine function, but same thing with the cosine function, right? If you have the cosine function starts up here and then goes down, 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 and up, and up. So same idea, it's going to oscillate through, and I should probably draw this. It keeps going and going. Like that. Okay. So, right, the sine function itself is not one-to-one. So what we do is we restrict the domain until it is one-to-one, and that's where the inverse sine function is defined. So we restrict the domain of sine of x to a region where sine of 1, and that is where the inverse sine, so the inverse of the sine function, and that is where sine inverse of x, right? Also known as arc sine, if you want to call it arc sine, that's fine. So that's where the sine inverse, I'll usually call it sine inverse. Sometimes I throw the arc in there, but I'll usually just emphasize that it's the inverse. So, and that's where the sine inverse is defined. Okay. So what we do, and there are specific regions that we define our inverses on. Okay. First one I'm going to copy is this one here. So the sine of the sine of x looks like this, and where we've kind of chopped it off at to span from -1 to +1 on all our outputs, because those are all our possible outputs, right? We've restricted the domain to be between negative pi over 2 to pi over 2, whereas for the cosine, we restrict it a little bit differently. The cos of x, oops, we restrict it between 0 and pi, right? And so here we've restricted the domains to different regions, right? But when we restrict it, it is 1-to-1, right? You can throw a horizontal line anywhere here and it'll pass the horizontal line test. Same thing here. Even the tangent function, which we'll talk about, which looks like this, we restrict the tangent function. Let me just scoot these over here a little bit. Oh. Okay, so the tangent function, remember the tangent function, and you can graph it in Desmos if you want, but it has this type of behavior at regular intervals, right? At intervals of pi. So between negative pi over 2 and pi over 2, notice that tan of x is not actually defined at those asymptotes, and then it just cycles over and over again. So you've got this behavior cycling over and over side by side forever. So what we do for the tan, to find the inverse of the tan, we restrict the domain to be between negative pi over 2 and pi over 2. Notice that it's not including those endpoints, right? Because you've got those asymptotes there, okay? So what this looks like is, let me just grab these shortcuts here. So what we say is that the sine inverse of x, if you force it to be y, right, the inverse function has outputs between negative pi over 2 and pi over 2. Okay, so the sine inverse looks like this. Like this. Draw it in a different color. So what happens is, now I find it hard, right? But we did say that the inverse function of a graph is the reflection around the y equals x line. And so I find that really hard to visualize. I don't know about you, but so what this ends up looking like is like this. Okay. So it's reflected here. This kind of, oops, this kind of flips up and this kind of flips down, and it goes between, so it has a domain between 1 and -1, or rather -1 to 1. Remember, so here, this is at -1 and this is at 1. The original function has a domain between negative pi over 2 and pi over 2, and a range between -1 and 1. The inverse, by definition, has the domain and range that are opposite of that. Okay, so because it's the inverse, it has a domain from -1 to 1. Okay, so this point here is at -1, and this point here is at 1. I guess I should put it the same. And the range is the same as the domain of the original function that we restricted. So from -π/2 to π/2. Okay. Same thing. So here, this is at π/2, and this is at -π/2. Oops. How about that? And I'll just close these dots to show that that's where they are. They're equal to those points. Same thing with the cosine. We're talking about the inverse cosine. The graph of the inverse cos looks a little bit different because it starts here at 1 and then it goes kind of this, oops, different color. It starts here and it goes kind of up to here. The domain for this thing is going to be the same as the range of the original function. And remember, the range for cosine, it's bouncing between -1 and 1. So again, it has a domain between -1 and 1, including both endpoints. Okay. And the range is going to be the same as the domain of the original function, which was, we were forcing it to be between 0 and pi, including those endpoints, right? So here you're at 0, and this endpoint here, let's say it keeps going here, is at pi. Clean that up just a smidge. Okay. Good. These are not things that I expect you to remember, but we need to talk about them just so that we don't have to spend so much time introducing them later. But just remember that we have talked about it, and that's good enough for me. Okay. So finally, for the tan inverse, the inverse tan is kind of the most interesting function because it keeps going, right? So it keeps going to -infinity and up to +infinity. So when I reflect this across the diagonal, okay, what this thing ends up looking like is actually kind of nice looking. And so let's talk about the inverse tan. Right, the tangent function is kind of nasty on its own. But the tan inverse ends up looking like this. Okay, and it's got these asymptotes here, of course, but notice that it keeps going and going and going. And so that's a nice property, right? So we've got these, it's restricted because it's got these horizontal asymptotes now, right? Instead of vertical asymptotes, we've got these horizontal asymptotes, but it is continuous throughout this region, whereas here, sine inverse and cos inverse, we're just restricted to these little blips, right? And so that's not very fun to deal with. But here now, we're able to put in any value of x and get an output. So the domain here is the same as the range for the tangent function, and the range is not including -π/2, but because we've got that asymptote at pi over 2 and negative pi over 2. Okay. So here, this is at pi over 2, and this is at negative pi over 2. So the inverse tan, or the arctan, is kind of the nicest one of all of these, with this nice property that we've got the set of real numbers as our domain, right? So that's nice to have. All right. That is the end of chapter 1. I do want to dip into chapter 2. Chapter 2, we're going to start talking about limits. Now, just as a kind of a spoiler alert, limits are not usually anyone's favorite part of this course, and that's okay. No one likes limits, so don't feel bad if you don't like them. If you like them, then that's great, but also weird. No. But we need limits later on, and so that's why. But if you don't like limits, don't worry. It's only in chapter 2, and then we'll just kind of poke around with them as needed afterwards. Okay? So let's see here. I don't even know what chapter 2 is called, but doesn't matter. 2.1 I know is called the tangent and velocity problems. So what we're going to do is we're going to start introducing tangents. Now, tangents are, and we'll talk about them more, but they're just straight lines that touch the curve at only one point, right? And so the slope of the tangent line is going to be an important player throughout the rest of this course. And that is going to be the derivative. So when we get there. For now, we're just going to talk about what it is, how it behaves, how can we approximate it, okay? But the tangent and velocity problems. So the tangent, the tangent line at some point on a curve, okay, is the line that touches the curve, but only at that one point. Okay? And so that's kind of a weird idea, but the tangent line at some point on a curve is the line that touches only that point. Only that point around the point of interest. The reason I say that is because around that point of interest, the reason I say that is because you could have a curve like this, right? And you might be interested in the slope of the tangent line at this point, right? And so the tangent line at, let's call this A, the tangent line at A is going to be the straight line that touches the point, touches the line only at that point, okay? And it might look something like that, but we also know that technically that's going to extend, right? So it's allowed to touch the curve at other points, but around A, it's only allowed to touch that one space, okay? So our goal is going to be to find the slope of the tangent line, right? So our goal is to try to find to try to find the slope of the tangent line and usually we want to find the equation of the tangent line, but ultimately what we're going to need to work for is finding the slope of the tangent line. So our goal is to try to find the slope of the tangent line. Now, if you think about the slope, right, the problem is that the slope, we usually denote it by a lowercase m. I'll clean that up, right? Y equals mx plus b, right? Typically we denote the slope by a lowercase m. And if you think about it, it has to be the rise over the run. The problem is that if you're only at one point, right, that's easy enough if you have kind of 2 points like this, right here at, let's say, A and B, right? Then here, the rise is this distance, whatever that is, right? And then the run is this distance. The problem becomes when we're only interested in 1 point, right? Because we're defining the tangent line as it can only touch this 1 point, right? Then we don't have a run, right? At a single point. So the problem becomes, the problem is we don't have a run at a single point, right? What we need 2 points on the curve in order to find the line, right? Or the slope of the line. Need 2 points in order to find the slope. Okay. So what we do is, okay, we say, well, to find the slope at exactly 1 point, I can't do that because my run from A to A would be 0, right? I'm dividing by 0, that's illegal math, right? So you can get there by doing that. But so that's a problem, we can't do that. What we do instead is we say, okay, if I have kind of a, well, let's do this. Let's use the curve that we just drew here. If I'm interested in the slope at A, what I do is I pick points close to A, right? And then I'm able to find the secant line. So the secant line is different from the tangent line because it cuts through the curve at 2 points, right? And so to approximate the slope at a point, or sorry, the slope of the tangent line at a point, the slope of the tangent line at a point we find the slope of the secant line. We find the slope of the secant line, which cuts through the curve at 2 points. Cuts through the curve at 2 points. And then we move closer and closer. So then we move that point closer and closer to the point of interest. We find the slope of the secant line between 2 points moving that point, moving the second point closer to the point of interest. Closer and closer to the point of interest. Okay. So what that's going to look like, let's go back and kind of use this one here as an example. So let's say I want to find the slope of the tangent line at this point A. Okay. What I do is I take a point here, or maybe I should, just to make it a little bit easier to think about, and call this point B. What's to the right or what's to the left of A? I don't know. Negative A? No. Right, so what I do is I find the slope of the secant line, right? And what I'm gonna do is I'm gonna move this point B closer and closer and closer to see what the behavior is as I move of the slope as I move this point closer and closer. So this guy is gonna move closer this way. And I'm gonna find the slope of the secant line at each point, right? And so I'll be able to find the slope of the secant line, but it means having to calculate the slope at multiple points, right? So if A is 2, right, then I might start here at B is 2.5. So find the slope between A and 2 and 2.5, right? And then I might move it closer to, get rid of this reminder here. Then I might inch it closer and say, okay, well, I know what the slope is between 2 and 2.5. What's the slope between 2 and 2.1? 2 and 2.01, right? And so getting closer and closer and closer to 2 or A, whatever A is, but not at A, okay? Because we need a little bit of distance in order to have some sort of run, okay? Okay, so let's do, I think we have, let's just do this problem here, or we'll start this problem maybe. So find an equation of the tangent line. To find the equation of the tangent line means that we're gonna have to find the slope of the tangent line, and that's the pickle here. To the parabola y equals x squared at the point 1, 1, right? When x is 1, the output is 1 squared, which is 1, right? So on the graph, we've got, what we're gonna do here is we're gonna have, here's our parabola, right? Y equals x squared. And we want to find the slope of the tangent line at x equals 1, y equals 1, right? So what I'm going to do is I'm going to find the slope of the secant line, right? So picking points on the parabola and connecting them with the point that I'm interested in. And then I'm going to slide this point Q, which is at x squared, right? X is x, y is x squared from the formula here. And then I'm going to slide this x closer and closer to 1, but not being equal to 1. So if you went through and you calculated these things, just because I'm running out of time, we'll do the actual problem next day. But just so you've seen it, right? What you would find is, and you can work through it, and I encourage you to work through it on your own. But if you let, so we can let Q kind of slide down from the positive side, or we can come up from values less than 1, right? And so here we're coming from the top and we're sliding down closer and closer to 1. And what we're finding is that the slope, which you know how to calculate, right? The rise over run, slowly gets closer and closer to 2, right? And then we can do the same thing. We can go from x equals 0 right? X equals 0.5, X equals 0.9, 0.99, and the slope is approaching 2, right? And so it looks like we see that the slope is approaching 2 as we get closer to X equals 1 from both sides, or from either side, I should say. So that idea of kind of moving our secant line and getting closer and closer to the point that we're interested in, that's the idea of limits. And so that's what we'll be working on in this chapter. But I know I'm out of time. And so since we just touched on this, I might do one little tiny question on the quiz, but nothing major, because we haven't actually done a problem yet, right? But maybe the idea of the tangent line and the secant line. All right. Any questions before we go?
Might have had some, but I don't think I have the brain cells to formulate them.
That's all right. I'll be here for office hours, so if something comes to mind, then I'll be back in here in 10 minutes. So just basically just 1.5 and this little tiny bit that we did, you know, the idea of the tangent line and the idea of the secant line for the quiz. I don't know, it's still scrolling. But pretty much it's a quiz on 1.5. Yeah, totally. Exactly, just great. All right, see you guys Friday. Oh, I guess I should stop this.